This section provides a brief introduction to normalization of databases. This presentation was organized by Dr. Farouk Alemi. The objective of this lecture is to learn about rules of good design. If the database is not well designed, then updates, insertions, and deletions could lead to anomalies in the data structure, and that could make the use of the database much more difficult. Normalized design improves efficiency, allows faster processing of the data. It reduces redundant data or data entered in different places. It reduces the need to enter missing data for situations where the data entry is not appropriate at all. For example, since a pregnant male is not possible, we would like to have pregnancy information kept in a different table than gender information, so that we do not need to enter blanks for pregnancy fields for males. Good design allows users to manipulate the database without knowing the physical location of the data. It should be possible for a user to search for a piece of information in one field and not have to guess what other fields may contain the same information. Update anomalies refers to the situation where the same information can be expressed on multiple rows. Therefore, updates to the table may result in logical inconsistencies. For example, each record in an employee's skill table might contain an employee ID, employee address, and skills. Thus, a change of address for a particular employee will potentially need to be applied to multiple records, one for each of his skills. In this example, once for public speaking, another time for carpentry skills. If the update is not carried through successfully, that is, if the employee's address is updated on some but not all records, then the table is left in an inconsistent state. Specifically, the table provides conflicting answers to the question of what is the address of the employee. Insertion anomaly refers to circumstances in which certain facts cannot be recorded at all. For example, each record in a faculty and their courses table might contain a faculty ID, faculty name, faculty hire date, and course code. Thus, we can record the details of any faculty member who teaches at least one course. But we cannot record the details of a newly hired faculty member who has not yet even been assigned to teach any courses, except by setting the course code to null. This phenomena is known as an insertion anomaly. Entry in the course table requires knowledge of faculty member who may not be even hired yet. There are circumstances in which the deletion of the data representing certain facts necessitate the deletion of the data representing other facts. The faculty and their courses table described in the previous example suffers from this type of anomaly. For if a faculty member temporarily ceases to be assigned to any course, we must delete the last of the records on which that faculty member appears, effectively also deleting the faculty member. This phenomenon is known as a deletion anomaly. In these slides, we will review several rules for normalization. Normalization is the process of applying principles of design to data structures so that they can conform to our expectations. The first rule we would like to remember is that each table corresponds to a single entity or a single relationship. You cannot have a table containing information about both the patients and the providers. Doing so unnecessarily adds confusion about where data might be found. It also forces us to add provider information when adding patient information, increasing the redundancy of the data. Always ask yourself, what is the table about? If you can tell it, it is about one entity and one entity alone, then you are on a good start to design of the database. The second rule makes sure that each row in the table is an occurrence of the entity and nothing else. A row in a table often is referred to as a record. Every record should be an occurrence of the entity. So, for example, in the patient table, each record should be one patient. If the provider table, each record should be one provider and only one provider. This seems very simple rule, but I have seen it violated many times. Consider a table of visits. Each record should be about one visit. I have seen occasions where multiple records are given to the same visit, or some records in the visits table are about the provider's characteristics. These are not reasonable ways to construct a table. Always check that the rows of the table refers to examples of the entity that the table is trying to describe. The third rule makes sure that the primary key uniquely identifies the occurrence of the entity. If we know the primary key, we should know which row in the table is involved. A primary key should not be used for two rows in the same table. For example, first name and last name are often insufficient for uniquely identifying a patient, as many patients have the same names. But a combination of first, middle, last name, and date of birth might uniquely identify the patient. A social security number uniquely identifies the patient. Rule 4 is to make sure that all fields in the table are facts about the primary key. If the fact is about something else, it does not belong to the table. For example, a name belongs to a table about patients. It's a fact about the patients. It's a fact about the primary key that reflects the individual patients. Likewise, date of birth is another fact about the patient and belongs to the table. But is diagnosis a fact about the patient? At some level, yes. But in reality, it is not just about the patient. A patient may have many different diagnoses at different times, so in reality, diagnosis is a feature of the patient's visit and not really a stable concept like what we put in the patient table. It's not a persistent fact about the patient. Therefore, diagnosis belongs to the table of visits and not to the table of patients. Rule 5 is to make sure that we do not present a fact more than once anywhere in the database. Many students think that data should be presented in the sequence found or reported so that it's convenient to use the data. But standard query language makes all data in the database available at all times. There is no need to duplicate the information. For example, it's not reasonable to list the names of the patient's providers in the visit table when the name is available in the provider table. We collect and often report who took care of which patient, but the information gets stored in different places. It's comfortable to have everything we want in a table. It feels that the data is accessible, but in reality, what we are talking of a machine, and all data from all tables are accessible to this machine. Therefore, there is no need to duplicate the data. We can avoid data anomalies by putting tables in the first normal form. A table is said to be in the first normal form if and only if all fields contain only atomic values and there are no repeating fields in a row. By atomic, we mean that it's not composite of two facts. For example, total charges is a composite of hospital and outpatient charges and cannot be a field in the table in this first normal form. By non-repeating fields, we mean that the same information should not be stored in two different fields. So, for example, diagnosis should not be stored in two different fields. For another example, if the patient has two diagnoses during a hospital visit, it is not reasonable to list them in the same row. In these circumstances, the recommendation is to list each diagnosis as separate records. Notice that each employee corresponds to a single row. Because an employee can participate more than one project, you have to put in few cells more than one projects and their name. Notice that the table lists the projects of Sheen in one field. Not a big deal. As a human, you can still read most information from the table and answer this question. Now imagine that you are a computer. How can you tell that P31, P32, and P34 means three projects? First normal form is violated in this table. When a database table does not have repeating groups, it is in first normal form. In other words, each cell stores only one value. You notice that in this table, some information is repeated, such as employee ID, name, and so on. So this table is not good enough, but it's still better than the previous table because at least some simple questions can be answered. The discussion of the second normal form requires us to introduce the concept of dependency. An attribute y is functionally dependent on an attribute x if a value of x determines a unique value for y. X may be a set of attributes or a single attribute. We show this as an arrow going from x to y and read it as x determines y. For example, we could say that an employee number functionally determines the employee name. This is the same as to say if we know the employee number, we will know his name. The reverse is not true. Knowing an employee name is not sufficient for guessing the employee number. So employee name is functionally dependent on employee number, but not vice versa. We need one more definition before we can state the second normal form. We say that an attribute is fully functionally dependent on another set of attributes if and only if it is not dependent on any smaller subset of attributes. An employee number may be fully functionally dependent on employee name and date of birth, as it is not dependent on either the name or date of birth by themselves. In this example, employee name is not fully functionally dependent on the attributes employee number and department, as it is functionally dependent on just employee number. Just knowing the employee number by itself is sufficient to know employee name. We do not need the additional information about the department. In essence, a fully functionally dependency is the smallest subset needed to establish functional dependency. In this example, ask yourself if street name is fully functionally dependent on employee ID. Well, it is not. If we know the employee ID, we still do not know where he lives. We would need to know both employee ID and address type to know where he lives. Now, we are ready to state the second normal form. A table is in second normal form if and only if facts in the table are fully functionally dependent on the primary key. This is a very important principle. It says that the primary key is the minimum subset necessary to determine each fact in the table. Here is an example of violation of second normal form. Employment and address cannot be in the same table as the ID does not fully functionally determine either one. In two separate tables, this is not a problem. The third normal form focuses on whether combination of facts can determine another fact. A table is in the third normal form if and only if there are no combination of strictly informational fields, that's not the primary or foreign keys, that determines the value of another field. Here we see that the net deductible is functionally dependent on other facts in the table. Employer's contribution, charges, and copay provides us with this information, and we don't need to redo this as a separate variable. So to put this table into the third normal form, we need to drop the composite piece of information that refers to the net deductible. Normalization is the process of applying principles of design to data structures so that they conform to our expectations. So far, we have discussed different rules that put a database in normal form. Database design is more than listing of fields and includes judicious designs about tables and their relationships. Tables that are properly normalized can be exploited by a wide variety of end users who do not have to be familiar with the structure of the data. We provide here rules of design and principles of normalizations that we encourage you to follow. Normalization of data structures improves efficiency and use of databases.